Yo, yo, yo. What's up, everybody? Welcome back. Today, we are trying to read joystick inputs from this guy in our Xbox controller. So, we're making an Xbox controller. The reason is mostly just because we feel like it, right? There's, minor inconveniences that I found on other controllers, and I'm like, I want to fix them. And so we're like, obviously, now we just make our own controller. Um, and so today we're looking at the joysticks. So, um, I wanted Hall effect joysticks, which are not like trivially purchasable through like, uh, DigiKey, or LCSE, like these like shops that sell chips to you, right? On LCSE, the like Chinese get Chinese parts website, you can buy joysticks for sure, right? They have like these like joystick modules. Joystick, probably singular, is what I want to search here. And they have something that like resembles what I would want, right? Something like this. But as far as I could tell from browsing this, they're all like potentiometer based. Where potentiometer is like, let's close all this shit. Hold on. Potentiometer is essentially like you got your stick, right? He's like in a box. In this box, there's like a hunk of metal like this, and this stick kind of like touches the metal, right? And so when you like pivot it this way, this stick moves up this way, and when you pivot that way, this stick moves up like this, right? And what happens is if you like connect one end of this to ground and one end of this to like, high voltage, like your I don't know what the digital high, I guess you'd call it. If you read out where the stick is touching, you're gonna get some value between these, right? Because like the metal has to like dissipate all of the voltage going through it. This is connected to ground on one side, so you're basically just like sampling this like constant dissipation of power, right? Now the problem with these sticks is you end up with stick drift because like you're taking a metal rod and like shoving it, like just scraping this thing with it, right? And then eventually that means that like the resistance of this thing will become like uneven, and your like previously 0 point will now have like some different value, right? That's my understanding. I don't really know how true this is. I bet you could like work around this with software in some way, but my understanding is that this is where stick drift comes from most of the time. You could also get stick drift because this stick is like got some springs that are like holding it in place, right? And these springs could like degrade over time, but my understanding is that like the vast majority of the time it's because of like this, right? So I want something that uses magnets, right? Because the magnets, they don't touch, which is pretty sick. And so that's how we end up with this guy. I Google Hall sensor replacement PS5. Now, what this means though is that like I don't have like a data sheet or a schematic for this thing. We kind of have to just like freeball it and try to figure out what's like the best option, right? So we know the one piece of information that we have is that this thing will plug into a PS5 controller. I managed to like take this thing apart and look at like some like labels on the chip. It didn't really go anywhere. I couldn't find a data sheet that's like associated with the things that are in here. So my thoughts are, let's just do what the PS5 controller does. We'll present that same interface to this thing, and then we'll know it'll work okay. And then also when we buy more of these modules in the future, we'll know that like even if they change implementation of like what they did in here, it will always work if they're supposed to go into like this environment. We'll like replicate the environment. So I Google PS5 schematics. Not PS5, DualShock 5, the name of the controller. Right? And if I click the like one of these links, and this guy has taken some pictures of this board. And this is the interesting one here. So this is like the backside, right? So it's kind of like the same view as this view here. So here we have like 1, 2, 3, 1, 2, 3, and then 1, 2, 3, 4 here, and 1, 2, 3, 4 for like the metal case, right? So there's this metal case, he's grounded, and then there's 2 outputs from the Hall sensors on each axis, and then there's a button over here that is pressed when you click the stick down. And you can kind of infer a bunch of stuff from this, right? If we look at this guy, so we know that these pins here are one of the sensors. These pins here are another one of the sensors. We can just like look at that from the picture. we can look at these guys. 1, 2, 3, 4. All 4 of these are like the metal cage of the guy, and then that leaves these parts here as the button that's pressed when the stick is pressed in, right? And if we want to know what the pinouts of these analog sensors are, we can take some pretty good guesses by looking at this board, right? So if we look here, this is a pin for the metal cage, and you'll notice that it's kind of just like allowing it to connect to like the whole world, right? Same with this one and this one and this one, right? You see these like little like hatches here that just go out to like the main segment of the PCB. My understanding is that it's common to have like a ground plane where you kind of like, okay, PCB construction. My understanding of this is like pretty limited, right? But my understanding of like how a PCB is made is you like have like a sheet of copper, right? You're just like, copper, please, just take your aluminum foil, slap it down, right? And then like some machine with like a knife or a laser or something like cuts paths through this thing, right? So if you just like you just cut this thing here, now you have like all of the outside is connected and then all of the inside of this is connected, but they're not connected to each other, right? And so it's, I think, typical to have like your big thing that's not like your big chunk of stuff to be like ground. You just like put everything that's not supposed to be a specific connection, you let that be ground. And so that's kind of what you're seeing here, I think, is that like these guys are just like this whole area, like all of this and all of this and all of this is just like ground, right? That's my understanding. And so that means that if we look at the sensor, that when you look at it this way, you're going clockwise. The most counterclockwise position on this thing is going to be ground. That's my guess, right? So that's one of the 3 pins. Here we see an interesting connection on this guy, right? This pin here, the most clockwise one, is connected to part of the button, right? So what's our guess here? Our guess would be that you have button connection to PCB, right? So you have like button, you press the button, and one end of this is either ground or 5 like voltage high, one of these 2 things, and then the other one is going into like the sensor, right? And so depending on whether or not this is pulled down or pulled up, you want this guy to do like the other one of those things, right? So we can assume that my assumption here, which could be wrong, is that this is connected to it's not the ground version, because none of these 4 guys are connected to the ground plane. They're all isolated, right? So if they were ground, they would just kind of like follow the behavior. They would look like this, I would think, right? I could be wrong, but that's what I would think. Which means also that like you wouldn't connect one of the joysticks here. That's fucking stupid, because this is like a sensor, right? This is like an inconsistent value, right? Which means that this is probably 5 volts, which means that, or like not 5 volts, 1.8 volts, it turns out on this board, like voltage high, which means that this is probably voltage high, which means that you're probably in this scenario where it's ground here, voltage high here, and then that leaves this as like the output, right? That's my guess. We read through this comment thread a little bit more, and we find that like all of the digital logic on this board is at 1.8 volts. And there's also some comments in that thread where somebody's measured the potentiometer output that used to be in here, and that potentiometer outputs between 0 and 1.8 volts, right? So we don't know what chip is in this thing and doing the measurement. We can probably make some guesses if we like just started reading data sheets for Hall effect sensors, but it's hard to tell. So we're gonna guess that it is something that resembles a potentiometer, has an analog voltage output from ground 0 to 1.8 volts, and this is the pinout. And I have confirmed that this works, right? So I hooked up these 3 pins. I put this to ground, this to 1.8 volts, and I put this into a like my multimeter, or like the my oscilloscope, I should say. And I did see that when I like rotate the joystick, we get it between 0 and 1.8. Pretty fucking sick. Okay, so that's part 1 of this thing, right? We've got this guy, we figured out his pinout, but now we need to read the values. So we've got joystick module, right? Boom, with known pinout on these. 2 of these pins just get like shoved on rails, right? So this is clockwise when looking at it from the bottom, which means counterclockwise when looking at it from the top. So this is 1.8 volts. This is ground, and this has to go into our like microcontroller somehow. The Raspberry Pi Pico, the board we're using, he does have a analog digital converter built in. There's a few things about this analog digital converter that we need to think about. One is that he says that if your reference voltage is less than 3.3 volts, or maybe 2.8 volts or something, maybe it was like less than 2.8, it loses precision. So we would have to drive the reference voltage at like 3 volts or something, which means that we're losing like half precision or something, because this thing will only ever input 1.8. And the more limiting factor is that the Raspberry Pi Pico, not the system on a chip inside, but the Raspberry Pi Pico board itself only exposes 3 ADCs. The system on a chip that we're using actually has 4, but only 3 are exposed to us right now. And so if we're going to follow the design of open source controller, right, you just Google open source controller and you click the link. I'm stealing this idea from them where they kind of just solder like the whole fucking development board onto their PCB. I'm like, I kind of like that. That's funny. Because I'm not going to fucking hand solder this little system on chip here. It means if we're doing this, we only have 3 ADCs on this guy, which is not enough for the 2 axes on 2 sticks. So where does that lead us? It means that we have to buy another chip to do like the 4th thing, or we have to use a multimeter. Or not multimeter, sorry, a multiplexer. And chat warned me that multiplexing analog signals is like asking for problems. So we look at the external ADC route. And it turns out that, the difference between a single channel ADC and a quad channel ADC is like negligible. So I ended up buying this guy, MCP3204, a 4-channel 12-bit ADC with SPI serial interface. And so we need to talk to this guy. So the setup is this guy goes into MCP3204. This guy outputs over serial a thing that goes into our Raspberry Pi Pico. Boom, boom. Right? This is the setup. And so today's task is basically trying to figure out how to do this. How do we read voltage here when it goes through this chain? That's about it. Yeah. So let's get moving and grooving. Long intro, but there's a fair amount of context that needed to be provided. Could reassign pins, but that would be annoying. My understanding is that I would have to straight or cut a connection and solder a new one on. That was my understanding, but I could be wrong there. I don't think that you can I don't think the pins are that configurable from the RP2040 perspective. Okay, so the plan of action is it turns out that the communication mechanism here is SPI, and this thing is dead fucking simple. Dead simple. It's 4 lines. One of them is pull low to use me, right? So we're gonna pull this thing low. One of them's data in, one of them's data out, and one of them's a clock. So the idea is that me as the Raspberry Pi Pico or the RP2040, however you want to think about it, I'm a master over here, right? I start I pull this chip select line down to say, I want to talk to you, sir. I send some stuff that's defined by the datasheet of this guy on data in. Um, Out of curiosity, do you know how much hardware is not exposed by the dev board? Not a lot. Not a lot. That one is like, I think that's like almost it, to be honest. I might change my mind later and just put the RP 2040 directly on the PCB that we make, and then we don't have to take this route. But maybe not. We'll see. I want to do this first, anyways. So we like send some stuff on data in that is according to the datasheet of this guy. He says, hey, if you want to read some stuff, you got to send me some stuff first. So we kind of do that. Here's his little example here. Then we read some stuff back, and we're clocking the whole way, right? Boom, 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 boom. Each clock cycle we send one bit, right? 0, 1, 0, 0, 1, 0, etc. Right? And I think that's like kind of it. So there is an SPI controller in the Raspberry Pi, right? But we can also just manually twiddle these wires. And I actually want to start by manually twiddling the wires because I believe that is simpler. It means that we don't have to learn how to use their SPI controller, but the downside there is that we have to use CPU cycles to do that, and we're probably like really limited on our maximum speed by doing it that way, right? The SPI controller can go probably way faster, but who cares, right? For testing, we can go slow as we want. So let's fucking bit bang this ADC, baby. Let's fucking run it. So let's look here. So we are going to have to set those pins up the way we want them. I think that's step one. So Raspberry Pi Pico pinout. So we have to ask the GPIO controller to set up pins 19, 18, 17, and 16 in the way that we want. So RX is going to be an input because we're reading. Chip select, we're going to handle that manually probably. Clock, so chip select and clock are output and TX are all output. So let's start there. Let's start by configuring those guys the way we want. So we probably have some examples of doing that somewhere. Here, init GPIO input. Nice. Do we have init GPIO output? That'd be kind of hype. Init LED is basically init GPIO output. So let's do that. We'll say we have input, we have output. Okay, so this guy, to do init GPI output, we're gonna initialize value to some value. So this is gonna be like, we're gonna write GPIO here. If initial value, we'll do a set. Else we'll do a clear. Okay. And then we use GPIO. Oh wait, hold on. These where I wrote GPIO here, this should be I fucked up. This is 1, 1, 1, GPIO, 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 GPIO. Okay, cool. Cool. Now probably we also have to set these like pads and stuff, right? But I guess most of like output disable 0, input enable 1. I think these are by default this way. Pull ups we don't, and pull down we don't have to configure because we're always driving, and then Schmidt and slew fast I don't care about. So I guess this is probably fine. So one SPI slave for each joystick. More like one SPI slave for all joysticks that has 4 ADCs on it. So we're gonna rotate through. We're gonna ask the slave for all 4 inputs one at a time. Basically, that's my my thought. Okay. Okay. So this guy's mad because we have to do like as E32. Like, do we have to do this for this to work? Yeah, we do. If initial value is equal to 1 here, as U32 like this, and then are we chilling? Yeah. Okay, cool. So maybe we're going to do something that's like init bit banged SPI. Okay. And here we're going to take 6 maybe we like wrap this in a structure for now. And we'll say, you know, RX is 16. Chip select is 17. Then we have clock is 18. And TX is 19. And maybe we put this in like pins. You know? Then we can do like init. And we're gonna say like set init GPIO input on pins RX. And then init GPIO output on the rest. I think, right? So chip select, clock, and TX. And then we probably want, I think it's chip select is low if we're selected, so we drive it high initially. Clock, it doesn't matter. And TX is probably also doesn't matter. Now, this thing I think is actually going to make sense to be a structure that like has data inside him, right? So maybe we say like current clock is a U1 and we do like init clock is 0, init you know, init tx is 0 or something. I think that's actually fine. I think clock is really the only thing that we're gonna have to think about. Maybe this guy's gonna get like a queue of stuff. Not really sure, but at the very least, it would be nice to be able to be like clock, like step. We'll have to think about it. Let's come back to this. We'll figure this out later. So let's just see if these GPIOs are set up right. So we should be able to read. Let's like set all these to 1, read them, and then set them all to 0 on the next run, and see if that gives us anything. How about that? How about that? So in main, we should be able to be like init bit banged SPI or something. Is that what we called it? Bit bang. What do we bit banged? Oh, it's bit banged SPI in it. Like this. And let's just take a little peek skis at what those values are. So I think we just run this. We need to run OpenOCD to do the programming. And this needs to be running in the right folder. Okay, so we run this guy, and then we hopefully see our breakpoint. No. That's interesting. So USB clock is broken since last time we were here. That's not good. We also probably should have saved that stuff, huh? So all of, oh, we did. Okay, so I don't know why that's not working, but also it's not important for today. So it's probably that we like forgot to turn something on that we were supposed to, but I'm just gonna do this. Oh, probably because this has to go after the X oscillator. Yeah, there we go. Okay, there we go. Okay, so what I want to do is I want to look at the values of all of those guys. So I'm going to turn on the oscilloscope and just quickly check all 4 of those pins and see what happens. I guess the 3 that we set to outputs are the ones that I want to check. So that's GP17. I guess I need like a wire to shove into this breadboard. And let's just see. So I'm going to probe 17. If I can connect these wires. God damn it, please. Please, God, please. Okay. Connected. Okay, and this is reading 0, which, let's just double check what we actually set these to. I forgot. So we set these all to 1, which I do not believe I am seeing here. Which is not good. Not good, but it could be because the pins aren't all the way in. In fact, that is what it is. The board just wasn't plugged all the way in, which makes sense. So 17, I'm seeing a 1, which is hype. Then if I plug into 19, 1, and then I plug into 20, all three of those guys are outputting 1. Or sorry, 17, 18, 19, all three outputting 1. That's hype. And if we restart this guy and set these to 0, and just run it again, I see it reset to 0. Just check all three. 0, 0, 0. Okay, cool. So that seems to be working the way that I would expect. Definitely need a desk cam. Yeah, that would be nicer. But whatever, you know, it's just occasionally. Occasionally we have to do this. It is what it is. Okay, so this is correct. It would be nice to prove that we can read from this guy. So when we our read is set to pull up by default. Is that what we want on the guy that we are talking to? Let's see. So D out this guy. It looks like they expect pull up here. Yeah. So that's cool. So we pull up here, and so we should just test that if we were to read this guy, we get ground, or like when we read and nothing's connected, we should get a 1, and then if we ground him, we should get 0. Yes. That's what we should expect. So how do we read from these GPIOs again? I don't remember, but I'm sure there's an example somewhere in here. Init GPIO input. This is used. Oh, it's just like this. Okay. So we can say that this is the RX is bitbang SPI SIO GPIO in shifted right by bit banged SPI pins RX, and we do this and 1. Yes. So we're hoping to see that RX is 1 here, which it is. Hype. And then if we set it so that we pull down instead of pull up, we should see 0. But we don't. So that's not good. Oh, but he is connected to the other side, so maybe... Maybe we have to be a little careful there, because this is connected to the chip, so who knows what's going on over there. So we will... Oh. Wait, hold on. it's because I changed the wrong thing. That's why. It's this one. 0, 1. Let's try that. That's 0 now. Hype. Okay, so that is working the way we expect. Okay, so our pins set up correctly. Now, what is the communication protocol to this guy? He expects us to send serial communications. So basically, this guy says, in a lot of words, this chart. So he's expecting us to be kind of clocking this guy. Boom, 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 right? We are going to clock down, change our value, clock up, and he's going to sample it, right? So we clock down, change, clock up, sample. Clock down, change, clock up, sample. I believe. Let's double check that. Sample. Or like down. Clock. The first clock received with this will continue blah blah blah. You're right. Data is always output from the device on the falling edge of the clock, which means that we sample on the rising edge. Right? So it means that data is always output from the device on the falling edge. So in terms of how we manipulate the data then, it's like clock, like down clock is we, clear one shift to the left by pins clock. And, or I guess all this like clock up and clock down. So on clock up, we set it. And then on clock down, we clear, right? And so what I'm a little bit confused about right now is, do thing, like if we were to like set value, clock down, and then read value, clock up, is this the loop? I believe it is, right? Right on falling edge. So when the clock goes down, that is when the value should be set. I think that's how it's supposed to be. So if we were to do like write bit or transfer bit, I guess, is the good name for this. We take the value that we're writing, which is a single bit, and we're going to return the value that we read back. I think that makes sense. So here we do like GPIO set if we are setting the value, if the value is 1, we set the pin at pins tx, and else we clear it. Okay? Then we clock down, right? Then we read, then we clock up. Is that correct? I think so. So we read this, shifted right by pins RX and 1. Or I guess this is just a truncate. Okay, then we clock up. That seems reasonable to me. That seems reasonable. We might need to put some busy wait in here. Maybe need to hold low for some period. That seems likely to me. So, but otherwise, I think we're fine. Yeah, maybe we do like a 402. Was there like a due weight that we have in here? There is. So we should change this weight to be for some period. And it's like 40. The clock is running at 12 megahertz. Which means that if we want to wait for like I don't know, in nanoseconds? Is that the right unit here? Microseconds is probably nanoseconds? Sure. So that's 1 gigahertz for nanoseconds. So if we want to wait for like 100 nanoseconds, that's 1 over 12 megahertz, period, over 1 over 12, right? Yes? That's how many. Is that correct? Is that how many ticks that we have to wait for? So say that we say we want to wait for 1 second. The number of ticks should be 12,000. So 1 over 12,000. So, but that's if this is in seconds, which it's not. This is in nanoseconds. So is that right? Can we do this with algebra? That seems like way better. So we have num ticks times num ticks nanoseconds times we have a unit of 12 million ticks per second. So if we want to figure out equals n ticks is what we're trying to get to. Times n ticks, I guess. So this multiplication doesn't work. So this means that we need like 1 over num ticks nanoseconds times seconds per nanoseconds. That doesn't sound right either. I'm why can't I like put the numbers in my head in the right order? So 12 million ticks per second times time, ns times, some time is equal to ticks. There we go. That's what we're looking for. So we get in period times period seconds, which means that we need to convert this from nanoseconds to seconds. So this is divided by, times nanoseconds per second. Period in nanoseconds times seconds per nanosecond. That's what it is. Yes. So that gives us 12 million divided by 1e9 times period, which is the answer that we got here. Yes. And so that says if we have 100 nanoseconds, Does our Spidey sense work? 12 million divided by 1 billion, right? But then we're doing so for a period of 100 nanoseconds. No, wait, we just do the sanity test of fucking 1 second, which is a billion. So we say 12,000 times a billion divided by a billion is 12,000. Yes. Yes. This seems right to me. I'm pretty sure this is right. So needed ticks is 12 million or 12 million times period ns divided by 1e9. Yes. 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 Okay. So then we go 0 to needed ticks over 255. Boom. Boom, boom. I think that's right. So if we put in here 1 million, I should see the LED blinking at approximately once per second, if this is all correct. Oh, interesting. Needed ticks, which okay, which this is doing. I don't know if you guys can see it. 1 Mississippi, 2 Mississippi, 3 Mississippi, 4 Mississippi. Like, that's about right. Pretty sure that's right. 1 second over 12 million ticks times 1 billion nanoseconds per second is 83.3 nanoseconds per tick. Yeah, I guess that's just the inverse of what I did. If I'm looking for a number of ticks to finish time, but I think it's the same. I think this is fine. I guess we'll leave this in. Yeah. Okay. So now we should be able to when we toggle the clock, hold it low for some known amount of time. So if we want to run at like minimum 10 kilohertz, it's like I think it was in the range of 10 kilohertz to 1 megahertz is what this guy said his like timing constraints were. So say that we want to run this at 500 kilohertz. That's 2e negative 6. Which is 2 microseconds, which is 2,000 nanoseconds. I think. 500 kilohertz period is 2 microseconds equals 2,000 nanoseconds. I think that's right. Sounds kind of right. Sounds kind of right. Fuck it. Okay, so now what we should be able to do is we should be able to send out like the stuff that he wants, right? So we should chip select here. Or I'll say enable chip select, which this should be 1 by default, I forgot. And then it looks like we kind of want the clock to be sitting high by default as well. I guess select chip is going to be like clear the chip select like this. deselect chip is just the inverse of this. Okay. Right. Cool. So then we do like our like read bits. We're gonna transfer bit of start bit, which he says, so this thing's like sitting there. We pull chip select low. So we select the chip. At the end, we deselect the chip for sure. Then we clock in the start bit, which is high. So we say transfer bit 1. Don't care what we get back. Then we have to choose whether we want differential pair mode or individual line mode, which I think is individual line mode. So we set, what does it says? Not differential or SGL. So 1 for single, I think. Don't you need one more do wait? Yeah, I'll put that in here, I think. I agree. I guess we could just put it here. And then maybe this is 1,000 to make sure that everything is kind of at the same right time, I guess. Sure. Maybe it makes sense to do it. Doesn't really matter. Okay, then we need to punch in the next 3 bits of like which channel to read from. 0, 1, 2, or 3. Right? So let's read from channel 0. So we just clock in 3 times. D2, D1, D0. So this is start bit. This is single mode. This is address 0. And then we need to wait for 1.5 clock cycles. So we just do transfer bit twice. Discard. Give it time. I think. Down, up, down. Then he gets the null bit here. Then we read 12 bits. It does matter. You want for some time for data to settle before it's read. And you want to give time for data to be read before it's overwritten. Yeah, true. So it's probably better to be like this way. No. I think it's fine. I guess we'll see. Because I do see how this could be bad if we're like set this down and then immediately clock down and read. Like maybe there should be a little bit of a wait before, like after that. But I was saying that there's no difference between if this is here or not, right? Like maybe you want something in between here or something. Not really sure. We'll hit the scope and we'll figure it out. Except I think I don't know if I have 2-channel scope right now. Do I? I don't know if I have like the wires for the other channel, which might make this harder to test. Oh no, they're there. Okay, we'll see. Ideally, you'd slice a full cycle into 4 segments instead of 2. Set clock, read clock. Yeah, that makes a lot of sense, huh? That does just seem smarter. Right, so you do like set the value, clock it down, then read the value, clock up. That seems kind of right. That seems kind of right. 2 is fine. Everybody writes on the falling edge. Everybody reads on the rising edge. Yeah, I guess it depends on what they mean by with CS low and DN high. I don't really know like what they're doing here, but that does line up with like the picture, huh? That like, oh yeah, because this is T sucks. What's T sucks? The amount of time that we have before read is probably what that means, right? CS fall to first rising clock edge. Ah. Okay, so and this needs to be at least 100 nanoseconds, and we're waiting 500. Okay. Which means that actually doing it with a leading 500 makes sense here. So on the first write, we will wait for like that chip select to have gone low for a little bit. Sure. Now, I'm not convinced about needing to wait 2 clocks here. But it is what the picture says. So we get null bit, then we should read 12 times to get the data back. So here, if we're like 0 to 12, we do like ret or equals transfer bit with I don't give a fuck shifted left by I. Is it because it's most significant bit first, so shift left by 11 minus I. Yes. Sure. Return ret, which means that here we should be able to return a U12 here, and we can call this like read ADC value. Sure, fuck it. That seems kind of reasonable. So if we go in here and we're like, while true, read ADC value. And we can log debug read value this. Okay. And let's just fucking see what happens. He's mad because 289, he's like, expected type U0 found U size. Whoa, as U12 here, maybe? Not bad. And then it casts here. Alright. And then can we like picocom here? And see what's going on in this world? So we are reading values that are different. So that could be because it's floating, or it could be because we're fucking everything up. So if I just like hard wire this pin to 0, do we see that happen? So Chris Titus Tech, thanks for the raid. What's up, you guys? What is up? To give a recap of what we are working on, I'm trying to make an Xbox controller, because it seems fun. It's kind of started with like a little bit of a brainworm, and now I just want to see if it's possible. Today's topic is reading joystick inputs from a thing I bought from the internet, a Hall sensor replacement stick for the PS5. Right, so we'll skim over some details here, but we've kind of like guessed a reasonable schematic or a reasonable pinout for this guy based off of like the some people's take apart of the PS5 controller. We are probably being a little over restrictive, but we're using 1.8 volts and treating this guy as a 1.8 volt ground and readout pin because that's what the PS5 controller does. We have connected this to an external ADC analog digital converter on the Raspberry Pi Pico. Because we need 4 ADCs, the Raspberry Pi Pico only exposes 3. The system on a chip in the Raspberry Pi Pico actually has 4, but they're not exposed on this board. And we're kind of copying these guys' approach of just soldering like the fucking breakout board onto the PCB because that's kind of funny. We might adjust this approach later, but anyways, for now, we need to use something external. So we are trying to talk to this guy, and we have just got to the point where we are throwing some data on the lines, and we have no idea if we have done anything correctly yet. But we are seeing that, once a second we're reading a value, but it's kind of just like a floating pin right now. So we're about to plug this thing in and see if we can get it to tell us 1 or 0 intentionally. So this is the top left pin, so I should be able to just bridge this shit. So if we kind of like, I don't know, you guys can like look down here if you want. I don't know if you're gonna really see much of anything. But I'm gonna take a pin here, and I think this is ground. So if I hard code this to ground to channel 0, do we start seeing that's like a relatively consistent 0 now, right? This is like very close to 0. And if I switch this pin to 1.8 volts, oh, that's not bad. That's not bad at all. I think that's a success. Shockingly. I was really expecting more pain there, to be honest. Because we didn't even check any of the lines with the scope or anything. We just kind of like wing-dinged it and hope for the best. So that's pretty sick. Pretty fucking sick. Okay, so the question is, this is supposed to be a 12-bit ADC. 2 to the power of 12 is 4096. So I think this is just working. That's fucking hype. So switch it back to 0 again. 1. Okay, so now what we can do is we should be able to plug in the joystick and just like fucking spin that shit around. Spin him right round, baby, right round. And we should start to see like values increase reasonably. So let's kind of put this in like a hotter loop. Okay, so we run this and we should see, oh, what is he pissed about? Okay, are you happy now? Bitch, complaining about constants and stuff. So now we're just spamming that fucking output. Hype. Okay, so now let's try to plug this guy in such that we are using the joystick. So it should be black wire go to black wire, black to black, red to red. Yeah, and then brown to ADC. So the ADC is kind of sitting over here. Let's not ground that guy anymore. Let's just plug this shit in. And what we should see is if I hit continue here and I start wiggling this guy around, we see 0 on one side to 2000 to 4000. That's pretty fucking sick. Yeah, that's basically doing what we want there, right? So as I push farther in, he gets closer to 0. Oh, we don't see it. Yeah, sorry. Forgot I was on full cam. So here, 0 to 0. Then we slowly ramp it back up to midpoint. And then slowly it's harder to pull it that way. But that's pretty sick. So that worked a lot smoother than I thought it would. Which is hype. Hype, hype, hype. Alright. So that's like bit banged approach working. Now, obviously, doing it this way is like stupid. But it proves to ourselves that we understand what like the format of this guy is, which is huge for us actually. So now what we would like to do is we would like to leverage the integrated SPI controller on the Raspberry Pi's system on a chip to basically do that for us, right? So what we're doing here is we're like asking the CPU, we're like, yo, CPU, could you transfer bit by bit? But that's silly because there's a chip that can do this for us. So instead, what we should do is we should write a higher level concept to that guy. So I think that's where we pivot to here. So this guy, you know, we've proven to ourselves also really simple protocol, right? We don't have to think about this at all. It's literally just like, you know, toggle the fucking clock, you know, set some data, clock it down, read some data, clock it up. You know, easy peasy lemon squeezy. So we now know exactly what's supposed to go on the wire, and we can just try to configure the chip to do that for us. So, Raspberry Pi system on a chip, RP2040. Surely this is open. No? Did I actually close it? That's crazy. What am I doing with my life? So this guy, SPI, has an SPI controller. He's, you know, supports working in master mode, and slave mode. We only need to put him in master mode. Presumably, what are the steps to use this thing? It's probably going to be like using SPI controller. We didn't really think very hard about this. You don't have that chip pinned to your browser? I can type. Typing doesn't take that long. So it's probably like take SPI controller out of reset, set as master, probably use the Motorola SPI protocol, because this chip can speak one of 3 languages, but we only care about using this one. Its input clock is already configured, but probably configure the output clock would be my guess, right? Make sure that, like, because he's got like a 12 megahertz clock input, but we need to make sure that we're talking at like 1 megahertz or less. So we need to like clock divide that thing a little bit, which is a feature that this guy supports. And then probably like populate transmit FIFO with, you know, sequence resulting in a read. And, man, just buy control from Microsoft. That's actually where this whole journey started. I used to buy the Elite Series 2. This controller was decent. It has 4 paddles. It's okay. The firmware on this thing worked just the way I wanted it to be honest. These paddles were registered as extra buttons. Hell yeah. But this thing broke like once every 6 months. And so I was spending like $200 Canadian every 6 months. And it just like shat itself. So then I started buying this GameSir T4 Khalid. This thing is $50, Hall sensors, pretty fucking sick. Hasn't broke on me one time. But the firmware on this doesn't do what I want. And so instead of trying to buy a third controller, we're just making our own. You know? The point is not really to have a good controller. The point is to enjoy our, like, I think it's fun to be able to like manufacture a thing. That's just kind of cool. It's kind of fucking sick. What do you want the firmware to do? Literally just like have buttons. I literally just want like the paddles to be paddles. Oh dude, someone fucking or Kirsten fucking got the brainworm in my head that I might want to turn on gyro. Like I might want to add some gyro chips, but I was looking at the gyro chips that are available. And they're all like really hard to solder on the board, which means that I have to fucking like pay some PCB manufacturer to do reflow soldering for me. So I haven't decided if I want to go that route yet, but gyro is another option for something that I want to do. Open source it. Yeah, we will. It'll go on my GitHub for sure. Okay. Let's look at a reference, I think. We want to probably just glance at the SPI init stuff in the SDK. We're not using the SDK, but, you know, it might be useful to see what they do to make sure that we are, you know, correct. So they toggle reset on the chip. they pull this guy. They set the baud rate by using prescale and post divide registers on the input clock. They write the post divide here. They write the, where does prescale go? Here. So they write prescale and post divide, hype, then they re-enable SPI with control register 1. So they have control register 0, control register 1, and SR. Okay. Then they set the format. Okay. Hype. And they, what is this? Always enable direct signals. Harmless if DA is not listening. Okay, that we probably can skip that. Probably. We'll have to take a look at what those do. And then they enable SPI through control register 1. Okay. And then when they write data, I think it's literally just like slap some shit into the FIFOs. I'm pretty sure. Okay. So let's look at what our registers are that we're allowed to talk to. We got control register 0, 1, data register, status register, clock prescale, interrupts. We don't need to use interrupts, I don't think. So this is like interrupt stuff, DMA control, we're not doing that, and then peripheral ID registers we're not using. So it's literally just like, it's literally just these guys, all right? 1, 2, 3, and then data. Seems reasonable. Okay, so control register 0. Let's keep the key on. Let's set up our types. Actually, let's do that. So we have a kind of like fucked up system where we have a file registers.json where we kind of just like write down what these fields are and what like their bits, like which bits each field occupies, and this will generate a zig type for us that will do the appropriate bit masking and reading and writing so that we can like make sure that we're only doing 32-bit writes ever and like respecting reserved fields, not really modifying them, and making sure that we're only changing the things that we want to change type shit. So in here we say we are going to have a SSP control register 0, and he's got some fields, right? Hype. Who kind of are, we could type this out, we could do it by hand. I think typing it out is easier. So we'll do DSS is bit 03 inclusive. We got FRF, which is 4 and 5. We got SPO, which is 6. SPH is 7. And then SCR is 8 to 15 inclusive. Okay. What else we got? We got control register. Okay, well, maybe we should read what these do. So we got serial clock rate. This is used to generate the transmit and receive bit rate. Sure. Where this guy is an even value from 2 to 54 programmed through this other register, and SCR is this guy. So 1 plus SCR times this times that. So this guy is a 12 megahertz clock coming from a rock. Then we multiply this by, multiply by. I feel like this should be divide by. I would have thought. Can we look at the clock rate thing again? I thought this was divide. Because like we have some input clock and we can say clock every 4. Every 4 clocks generate an actual output clock. That would have been my thought here. But it's saying times, which is confusing. So first of all, we have to figure out, we have some things that are like known in like the Raspberry Pi Pico land, and some names that are known in the SPI controller land. We have to figure out how those are linked together. So S clock is the output clock. Okay. Then where do they talk about clock parry. SPI uses clock parry as a reference clock for SPI timing. This is referred to as SSP clock. So SSP clock is the 12 megahertz clock from the crystal. Then clock sys is used as the bus clock, also 12 megahertz for us. It's referred to as P clock. Okay, so P clock is our processor clock. SSP clock is the reference clock from clock parry. Gotcha. Okay, so we go back down. When configured as a master, we have two free-running, reloadable, serial-linked counters providing a serial output. Provides a serial output clock. You program the clock prescaler using this guy to divide the fast clock by a factor of 2 to 54 in steps of 2. The output of the prescaler is divided again by a factor of this by programming this guy. So it is divide. I don't know why it said times in the fucking register definition, but it is divide, right? Okay, so that makes sense here. So we're in the control register 0. This guy is one of those two divisors. Probably the second one. Then we have the phase of the output, right? So whether or not we're like clocking with data or this is probably if we're clocking, if where data goes out on down or up. And I think polarity was whether or not we're default high or low. I think. So if we look at the pictures for phase, I think they had pictures for us. Yes. So we were moving the clock, we were setting data, then moving the clock down, then reading, then moving the clock up. That's what we were doing in our bitbank version. So this is 0, 0. We go up, down lines up with data change, up, down lines up with data change. Okay, and then if we flip the phase, now it's up lines up with data change, gross. With polarity 1, S0, we have clock is up when nothing's happening, right? Here it was clock is down when nothing's happening. So what were we doing in our known to work example? We had clock up when nothing was happening. So we want SPO1, and this is changing data on up. So we want 1, 1. This is up by default, down when data changes. Yeah. So we want, init SPI. Okay, so control register 0. We want SPO 0 and SPH1. Okay, so let's look at that, go back to the control register, see what else is in that bad boy. So serial clock rate, undetermined. Okay. And then the frame format, we want Motorola SPI. So this is 0, and really this should actually be Motorola, which means that we need to, in our registers file, define a type for this. So we're going to say that on this FRF field, this is actually going to be a more complex type. And we're going to say here we have a, he's going to be defined by some type of FRF, probably, we'll call it. And this is his offsets, where this guy lives. So now we say we're going to define a type here, FRF, and he has, bit size of 2 bits, I think it was. And his fields are what? He's got Motorola at 0. He's got TI at 1. He's got microwire at 1.0, so 2, and then nothing at 3. Okay. So now we can say this is Moto, hype. Let's just make sure that if we build this right now, everything's happy. No. This JSON is not parsing. We did something wrong. Forgot a comma here. Okay, cool. And then DSS is data size. So we want 12-bit, which is 1011. Is that 12? That's 1 plus 2 plus 8. This is 11. Right? 8 plus 3, 11. Or no. Yeah, 8 plus 3, 11. So it's off by 1. Yeah. So I guess that's fine. So we want DSS, and we'll just use a number here. I think that's fine. I think that's fine. We don't have any way for us to like have like complex mapping of data this way, so this is fine. 12 minus 1. Okay. Control register 1. What's going on in here? 4 bits. Slave output disabled. This bit is only relevant in slave mode, so we ignore that. Master or slave select, so we want master mode. This can only be modified when the SSP is disabled. So we need to disable it, then set this, then enable it. And then loopback mode, surely off, right? Surely. So CR1, we want SSE off. Then we turn it back on later. And then we do SOD don't care. MS master. And then loopback mode off, right? And then here we need to define this register. So we have CR1 now, and he's got some fields on here that we got to define. So it's we're not going to use SOD, so we just don't give a fuck. We're not going to define it. We got MS at 2. We got SSE at 1, and we got LBM at 0. Then surely this is going to be like this is going to be loopback mode is going to be a complex type. Okay. Offset, what was this? LBM was 0. Okay, we got SSE. I think this is also going to be like an on-off type shit. So like this. And then MS was also complex type. We want master slave here, probably. So we do like this, and we have to define all these types. So we got enums. We got MS is fields are master and slave, right? Master, which is master is 0, slave is 1. Okay. Pipe. We need to define bit size here, which I guess is 1. Then we got SSE, which is also bit size 1. Fields are off 0 on 1. Okay. And then we got LBM, which was 0 normal, and 1 is loop. Okay. That seems reasonable. Does that compile? No. JSON problems. Where did we fuck up? JQ. He's mad at line 517, column 9. The fuck? LBM offset is missing a quote. Ah, true. Good eye. Thank you. There we go. Cool. Okay, so that compiles, and now control register 0, we've kind of figured out that all figured out. Data registers, you just write this shit to get something, read write it to put data in, read it to get data out. What is the transmit order? Most significant bit first or least significant? I think most. Where did it say that? Frame format? Was that oh yeah, here. It shows us MSB first. Right here. Which is what we want. Okay. So data and then status. Surely this is going to tell us when we can put things in the FIFOs. Do you do first order logic? I don't even know what that means. So who knows? Okay. So we definitely need to define this status register to tell us if we are busy or not. Like if we're ready to dump data in or not. SSP SR. So what we got in here? We got busy at I guess we should name it correctly. BSY. At 4, we got receive FIFO full. At 3, we got receive FIFO not empty. At 2, we got transmit FIFO not full. What a weird. Why would you have receive FIFO full, transmit FIFO not full? That's a confusing fucking API. I'll fucking say it. And then transmit FIFO empty 0. And then busy is if we're currently transmitting. Or the transmit FIFO is not empty. So we'll probably just ignore most of these and only look at busy. Probably. Zig build. Okay, so all of our types are generated, which is hype. So now we should be able to kind of make a SSP abstraction. We're gonna make it a function because there's technically multiple of these. And we're gonna say like, here's our like base address. This is where like this guy's located, and he's gonna return a type who returns a structure with the registers that we care about. So we have okay. So this is the first base. We got control register 0 is registers.sspcr0 initialized with base plus its offset, so 0. We got control register 1, which is base plus 4. We got fucking status register, which is base plus C. And then we got clock prescale register, which we didn't define, but that's fine, probably. Let's just do this as a volatile U32. I know it's not quite right, but fuck it. And then data register will also just say as U32. And data was at 8. And then we'll just say fix me not raw 32s, but whatever. I don't give a fuck right now. I think it'll work fine. Okay. So now when we do our SPI initialization, we need to figure out what our clock, prescale, and serial clock rates are. Right, so we want to be, you know, maybe like 500 kilohertz, right? So we want to do, we have 12 megahertz divided by 500 kilohertz is 24. So I think that we just put 24 in one of these guys and 0 in the other. I think that's fine. So SCR will put 0. And then we'll put, you know, it's probably kind of like this. Disable the thing, set CR0, set CR1, then set this guy to 24. I think that's right. I think that's right. Okay, let's just do that. But first we have to like take the thing out of reset. So that means that our register definition for the reset thing, he needs to know which one of these is the SSP controller. So can we look at reset space? Boom. Where does he fucking tell us? It's one of these is gotta be SPI 0 is 16. So we're like resets reset atomic clear to take out of reset of SPI 0. Okay. Then we say we actually need to. We made this function to make an SPI or an SPI controller, but we have to make SSP 0, which is going to be an SSP with a base address of something. So SPI, where are we at? SPI 0 base this one, and this is SPI 1, so it's this one. Okay. Okay, so now when we're like here, we go SSP 0 dot control register 1, modify and set SSE to off. And let's just start compiling to make sure that everything works. So can we do like init SSP init SPI. Okay. So that compiles, which is shocking, but kind of pleasantly shocking. So we turn off SSE. We set 0, to a combination of a bunch of parameters. So we're going to set SCR to 0. We're just going to copy paste whatever the fuck we set down here. SPO to 0. SPH to 1. So this is default clock high, data change on down clock. Right, that's what we said here. Maybe we will comment this like this. This is divisor, all handled by the SSP CPSR reg. Okay. Then this is, that's self-explanatory. FRF moto. That's pretty obvious what we're doing there. And then DSS of 11, and this is this is what is it? It's like ADC at 12 bits. DSS is bits minus 1. One of them had to be a multiple of 2, though. Don't remember which one. Yeah, but I think 24 is a multiple of 2, so not worried about it. Okay. Control register 1. We're going to be setting some sort of combination of some shit. So we're going to set MS to master. Master mode, self-explanatory. And loopback mode is normal. Don't loop back. Duh. I thought we arrived at 25, my bad. Maybe we did. I thought it was 24, but I mean, also it doesn't really matter. If we arrived at 25 and we just go off a little bit, it's like whatever. The period doesn't really matter that much. Okay, cool. So then we set this guy to 24. And then we turn it back on. That seems kind of reasonable. Close. We do need to pointer cast these. Or pointer from int these, I guess. Okay. Cool. So he's mad because I forgot we use kind of more complex types here. So this is on here. What else? That's about it. Nice. Nice. Okay. So then I guess what we should see here, if those are both divisors, is it okay that one is 24 and one is 0? The 0 is actually 1. Because if we look at this guy, it's 1 plus SCR. And then the other one is good question on this one though. Must be even number from 2 to 254. Default 0. Return 0 on reads. So I wonder if this is just like invalid if unset. That seems likely. But who fucking knows? Because he's saying just huck in a 2 to 254. So feels fine to me. Okay, so if this worked, we should be able to. Can you not check the clock speed with the Cody Royce array? I believe that this clock output is not connected to that, but it is worth checking. You're right. That'd be interesting. So I think his options for what the frequency counter can count. What was this, like FC0 source? None of these. Yeah, these are like PLLs and clock sources. None of these say clock SPI or whatever. And that's because I believe that kind of like the diagram is like we have, some clock sources. We have like the ROSC and like the crystal, we got like a rock or whatever. These guys, or PLLs, right? These are kind of like clock sources. These are fed into what, these like clock sources from the perspective of the Raspberry Pi Pico, right? So, or from the perspective of the system on a chip, right? So one of them is like USB clock, and one of them is like Perry. One of them's like sys and RTC or something. I don't remember all of them, but I think the way it's hooked up is that clock Perry goes into the SSP controller, and in the SSP controller there is like another clock here, and we have configured this guy, right? And the frequency counter here can only measure these, is my understanding, right? So because this is kind of like downstream of like the clock's subsystem, he doesn't like feed back in this way, I think. But it was worth checking. It was a good thought. Okay. So what we should expect to see here is nothing yet. And do we need to like initialize the GPIO pads? We totally do. So we also have to set the GPIOs. We have to say how do we want these guys to be. So for each of these pins that we care about, you have to say please fucking come from the SPI controllers. So I think this was 16, 17. What was it? Blop 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 blop. Is this the right guy? This is the Raspberry Pi Pico and Pico H. So we want GPIOs. God damn it. Why does Zoom never fucking work? We want 16, 17, 18, 19. And all of these guys should be using SPI, I think. So, like, basically we have to pick which one of these, like, fucking boxes it's pulling its value from. So we go to wherever the fuck that's defined in the datasheet. I think it's like funccell. Here, nice. So SPI is one of these fucking lines. Function 1. Okay. So GPIO funccell, we have UART2, I2C3, SIO5, and so we want SPI, which is 1. So here we can now go like all of these guys are SPI pins. Okay. And then probably I think that we still have to set like the pull up and pull down and shit. So we need to make sure that I think we only have to worry about inputs because all of these outputs will be driven, which will work by default. It's only the input that we probably have to be careful about, and maybe that he'll do it for us. But it might make sense for us to be like, you know, whoa, is this? Oh yeah, I see. So we might want to do one of these here for pin 16. Fuck it. RX pad control, we'll call it. And we'll just say pull up enable. Just for, peace of mind. Just for peace of mind. Okay. So then after all of this, what do I expect to see? Let's do like a while loop in here. And let's just try to like spam some fucking data on TX. It doesn't really matter if it's valid or not. We just want to see if like the clock will start running, right? So we probably want to read the status register. Which status register? So while this is busy, we do nothing. Then we try to write into the data register, the letter A or something, right? Let's just like slam some data at it. And hopefully we start to see something of interest here. Okay. So I'm hoping that I'm going to like plug in the scope here and start seeing like, I don't know, some shit. Hold on. Let's figure out. I need to get another wire. We'll try to flip this down so you guys can like at least pretend you're looking at what I'm doing. I need another wire here to ground the oscilloscope, which I don't have any just floating around. So ground the oscilloscope. Ground. And I guess initially we'll probably get away with reading the clock value. I just want to see that the clock is spamming, which is the 4th pin from the end, which is the yellow one here. So I think that lines up. Turn on the oscilloscope, which is not on right now. Give it a sec. Not that you guys can see that part. And good news, everybody. I don't know if you guys can see that, but he is just spamming some shit, right? Boom. So what that means is that we sure are like occasionally transmitting clocks, right? Which is kind of sick. The next one to look at would probably be the chip select. So we should be seeing the chip select go down and up like semi-rapidly, right? Every time we start a transmission, we should be like, yo, bitch, talk to us. So I think that's this one. Which, if I hold this guy down, I do start seeing like a square wave on this guy, right? Which lines up with like occasionally talking to him. Do we really say yo bitch, or is that sarcasm again? I mean, it's how I would say it. I like to anthropomorphize these guys. Which is hype for me. Okay. So then if we look at the transmit, and when I talk to people, I only talk to people who talk like me, right? So that looks like it could be the letter A. Maybe. We're really like flying by the seat of our pants here, but I'm going to go with probably correctish. And we expect probably that on read, we're not getting jack shit, right? So I think the next thing to do is to try to figure out how to write the correct thing here and read back something, and then figure it out from there. Okay. So I want to look at the reference again of the Raspberry Pi Pico SDK because I don't remember how they did reads and writes here. Oops. Read blocking. So they just did like Rx remaining is some length from the FIFO. They do like destination is equal to SPI get hardware. So he just reads the data register if it's readable. And this is probably like if the like the read FIFO is not empty. That's what this is saying, right? Read FIFO not empty. So that should be pretty straightforward for us to do, right? It should be like we write in something that resembles what we tried to write before, right? So we copy paste this 11000000. 11000000, right? We write that. And then immediately try to read him back. So wait for him to wait, and then we need to write one 12-bit value. Yeah, so this is the enable. This is what is this? This is start enable, chip select, 3 data selects, and then 2 clocks for wait, right? That's what we said before. Wait for him to like actually sample. Then he'll immediately start spitting stuff out for real. So that should be when we can start. Then we send him another value, just like give us the next 12 bits. And so I think we can just do this. While the transmit FIFO is not empty, wait, send some shit, then while the read FIFO is not empty, read a value. And then stood log info read val, which should only trigger once per. So then we should like assert if we read this guy again and the read FIFO not empty is true, it's not empty, we breakpoint because that's a problem. That would be a bug. All right. Let's see what fucking happens. Okay, so we are hitting breakpoint. Not great. At 360. Do we exit this thing ever? Yes. Oh, I guess we're reading once. We need to read once for this chunk of shit, then once for this chunk of shit. So the first read we should discard. And then the second read. So if this is not equal to 1, we have a problem. Then we read it again to get the stuff we actually care about. Is there a sleep like command once you call in a loop while busy reading? Yeah, like you could like try to put the processor to sleep if you wanted, but I think that it's you know, we're fine to just fucking slam that shit. Okay, so this is 359. So we are hitting this, which is I guess that makes sense if we are reading too fast. So I guess we should wait for this guy to not be busy anymore here. So we wait for him to fucking finish everything. Yeah. So while busy, chill the fuck out. Then, I think we should probably just fully reset this chip also. Uh, just to make sure that like we clear any state from a previous run, because I think that could fuck us here. So we say transmit FIFO empty. Yeah. So then we wait for it's busy. He finishes his shit. Then it should be if we kind of do this once. If there's not stuff in the FIFO, we have a bug. Discard the first chunk of response. Then, if there's not stuff in the FIFO, we have a bug. Then we read the response and write it out. Then, if there is something in the FIFO, now we're unexpected. We think we have drained it by now. So here we say this. Okay. Oh, that's fucking promising. 4,000 when I pull the joystick to the right, 0 when I push it to the left. That's fucking sick. That is fucking awesome. That actually went a lot better than I thought it would. Like, way better than I thought it would. I'm kind of shocked that this worked. That's so fucking sick. I mean, I know that the hardware is pretty straightforward, but it's pretty sick that we can just kind of fucking read the spec, YOLO some register rights, and just like, it works. That's honestly quite surprising. Like, it usually is more painful than this. So I guess that means that our intuition on this system on a chip is just getting better over time, which is pretty fucking sick. Pretty fucking sick. All right. So I guess that's it for today. We kind of have successfully talked to this ADC. The values coming out of this thing also seem to be like relatively stable. I'm quite happy with, you know, the level of detail I have when I'm slowly pushing this guy down. Right, that's pretty sick. You know, it seems to work pretty well. I guess the one thing that we need to check here actually is that we should be able to read from a second channel, right? So that we haven't tested yet. So here, if we wanted to read from channel 2, it would be, we should set this bit high, right? So if I run this now, it should not be working, right? So I move this thing and nothing really of value happens. But if I then switch the port of the joystick, then it's working again. Okay, cool. So this means that we can sample from multiple ports on this guy. Things are working okay. All right, cool. That's sick. Thanks for watching, guys. I think we call it there. If you like what you saw, we stream most days. You know, in the block of 12:30 to 4 o'clock Pacific time. It is 3 o'clock Pacific time now. Things went smoother than I expected today, just in general, so kind of happy with that. But it does mean that we're ending a little bit earlier than normal. So if you want to keep up with this project, swing back by in that time block. We also post to the YouTube implementation stuff, things that are titleable and thumbnailable get on the YouTube. The other components of the stream get published behind a paywall because unfortunately we do have to try to keep our friendly YouTube algorithm a little bit happy. So there are some things that I think are worth streaming but are not friendly to the algorithm. If you want to support the channel so that this content keeps happening, or to get access to that stuff, you can support on Patreon, sub on Twitch, or join as a YouTube member, and the remaining VODs will go up in those locations. This content will end someday, right? But that day is marked by when I run out of money. So, you know, if you want this content to continue, consider supporting in whatever way makes sense for you, but also don't feel any obligation at all. Because, you know, it doesn't matter to me. When I run out of money, I'll just get a job, you know? It's not the end of the world at all. I think that's it. I think that next steps on this project are going to be, we got to do some PCB design as well as a little bit of more hardware design. We've got to finish up the bumpers and stuff and figure out where all of the buttons on the PCB are going to go. Software wise, we got some USB stuff to handle. I don't. Yeah, I have to think about software side a little bit more. Ideally, I want to do a push for getting the PCB fully fledged, like flushed out, so that we can order a PCB and then the software stuff can come later. So we'll see how it goes. All right, cool. YouTube, peace out, and Twitch, let's find someone to raid.